today's class we are going to study about the generating function of Bessel function. Generating function of generating function of g and x, which is Bessel function. Bessel's function. Right. So generating function says that e to the power x upon 2 where z minus 1 upon z is equals to summation n tends to minus infinity to plus infinity z to the power n g and x. Right. So this means that if we compare the coefficient of z to the power n both the sides, we will get the g and x. If we remember, g and x was generating function, Bessel function summation r tends to 0 to infinity minus 1 to the power r whole upon factorial r factorial n plus r x upon 2 to the power n plus 2r. This is what we already discussed in our last lectures. So the generating function says this is the generating function for Bessel function. So when we compare the coefficient of z to the power n both the side, so we will get the j and x Bessel function. Okay, just to prove this, we will use left hand side expansion. Proof. So the proof is e to the power x upon 2 z minus 1 upon z. So if we treat x upon 2 z minus z as, so I can write it as what? This can be written if I just multiply xz upon 2 minus of x upon 2z. I can rewrite this as this. So e to the power xz upon 2 is equals to dot e to the power minus x upon 2z. So I can write this as in this form. If you remember, expansion for e to the power x is 1 plus x square upon factorial 2 plus x cube upon factorial 3 plus so on. So we will expand each term as e to the power x. So on the first term, we treat this as x. Alright, so we can expand with the help of this expansion formula. So for the first term, suppose this is first term and this is second term. So if I expand first term, so this says that this is on multiplication, so I use the square bracket. So the first term is 1, our x is xz upon 2 plus x square, that means xz upon 2 to the power 2 and with the factorial 2. Then 1 upon 3 factorial xz upon 2 to the power 3 plus so this will continue to, right, multiply by with the second quantity is our second term is e to the power minus x2 upon z. So for the second term the expansion becomes 1 plus our x, now our x is minus x upon 2z minus x upon 2z plus 1 upon 2 factorial, this is factorial, minus x upon 2z plus 1 upon 3 factorial minus x, this is square, upon 2z to the power 3 plus so on. Now if I have to compare the coefficient of z to the power n, so where I will get z to the power n, when the first term of z to the power n will get when if I expand this series to 1 upon n factorial x upon z to the power 2 n, alright, plus next term will be factorial n plus 1. Let me erase this. Factorial n plus 1 x z upon 2 to the power n plus 1 plus so on. So the equation goes on. Alright, this is multiplication factor. Now same we can write here, 1 upon factorial n minus x upon 2z to the power n. Just remove this. Plus 1 upon n plus 1 factorial minus x upon 2z to the power, this is 2z to the power n plus 1 plus the series goes on. So if we'll see closely where I can find the z to the power n, if I compare the comparing the coefficient, just right here, just write comparing the coefficient of comparing the coefficient of z to the power n. So if we compare z to the power n, so where I can find z to the power n, if this term multiply with this term, alright, so this will give me the first term, so this will give me what, factorial n x upon 2 to the power n. Why not z to the power n? Just because we are comparing the coefficient z to the power n. And next term where I can find the z to the power n, if I just multiply this term with this one, here 1 upon z to the power n is on denominator and here is z is on numerator. If I just multiply, so this will give me n plus 1 minus 1, so this will give me z to the power n. Alright, so second term will be minus of this, just because this is minus, alright, minus of 1 upon factorial n plus 1 x upon 2, n plus 1 is already here and 1 x upon 2 is here, so this becomes n plus 2 plus so on. If I multiply the third term with this term, so this will give me plus of 1 upon factorial n plus 2 x upon 2 to the power n plus 4. Alright, so this sequence, this series is nothing but the Jnx. If you remember, our Jnx was factorial r tends to 0 to infinity minus 1 upon r upon factorial r factorial n plus r x upon 2 to the power n plus 2r. This is 2. Alright. So we can say that on comparing the coefficient of z to the power n, both the sides, we will get the Bessel function Jnx. So we can say that this is our generating function for Bessel function. If you remember, we can compare the coefficient of z to the power minus n2. Now comparing the coefficient of z to the power minus n. So z to the power minus n, where I can find z to the power minus n? When this term is just multiplied by this term. So I will have the first term as 1 upon factorial n minus x upon 2 to the power n. Alright. Now where I can find the second term? If I just multiply this term with this term, because here on denominator we have z to the power n minus 1. So this becomes, when I multiply with this term, so this becomes how much? Uh, I can write z as minus n minus 1, and here is plus 1. This will give me again z to the power minus n. So we can write plus 1 upon factorial n plus 1 minus of x upon 2 to the power n plus 1 x upon 2. This is just, and here x upon 2, remaining x upon 2, plus so on. So just modify this equation. If I just take 1 minus 1 to the power n common from all these terms, so this will give me, the remaining term is factorial 1 upon factorial n x upon 2 to the power n minus of 1 upon factorial n plus 1 x upon 2 to the power n plus 2 plus so on. So if I look closely, this is this term. This series is our minus 1 to the power n is Jn. So we can say the above generating function, which e to the power x upon 2 minus z upon 1 minus z is equals to summation n tends to minus infinity to plus infinity z to the power n Gnx. So on comparing the coefficient of z to the power n will give me the Bessel function. So this is what the generative function for the Bessel function. Thank you.